Hey everyone, and welcome to this explainer on rotational mechanics. Today, we are going to translate what you already know about linear motion straight into the rotating world. So if you've been comfortable calculating force, mass, and acceleration on straight lines, well, get ready. We're about to take all those concepts and literally spin them in a circle. Okay, so to really grasp this, we first have to admit a crucial little problem with how we've been doing things. Real objects in daily life have finite size and shape, which means the standard point mass model just isn't going to cut it anymore. I mean, in earlier chapters, we treated everything from sports cars to literal planets as if all their mass was just squished into a single, infinitesimally small dot. But think about a spinning ceiling fan, or maybe a heavy cylinder rolling down a ramp. Their motion isn't just pure translation, where every single particle moves at the exact same velocity. It's translation plus something else. And to figure out what that something else is, we really need to upgrade our models. So here is our game plan for today's session. We'll be looking at 1. Beyond point masses, 2. The math of rotation, 3. Torque and angular momentum, 4. Mechanical equilibrium explained, 5. Inertia and rotational analogies, and 6. Conservation and final review.
Part 1. Beyond point masses.
Let's start out with the foundational rules for analyzing extended bodies in motion. To simplify a really complex reality, we use a neat concept called the rigid body. Now sure, no real physical object is truly 100% rigid because they all warp, bend, or vibrate just a tiny bit when forces are applied. But for things like solid wheels, spinning tops, or heavy steel beams, we can safely ignore that microscopic warping. By treating them as perfectly rigid, we basically assume the distance between any two particles inside that body stays exactly the same, no matter how much it spins or tumbles. This assumption is the absolute cornerstone of rotational mechanics.
So, to understand how these extended bodies actually move as a whole, we rely heavily on the center of mass. Think of it as the mass-weighted mean position of the entire system. Imagine taking a rigid body, which is really just a system of countless closely packed particles, and finding the one specific coordinate point that represents the average location of all that mass. It's pretty amazing in practice. If you throw a spinning wrench through the air, it looks chaotic and wobbly, right? But its center of mass is flying in a perfectly smooth, predictable parabolic curve, acting exactly like a point mass would. And calculating this is incredibly elegant. For a two-particle system on an axis, finding the center of mass takes just 3 simple steps. First, you identify your masses. Second, find their distances from the origin. Third, apply the weighted calculation by multiplying each mass by its position, add them up, and then divide by the total mass. What's super cool is that if you have two particles of the exact same mass, that math puts the center of mass exactly midway between them. And for homogeneous symmetric bodies, like a uniformly dense ring, a disk, or a solid sphere, the center of mass conveniently sits right at their geometric center.
Moving on to Part 2, the math of rotation.
Now that we've got our rigid bodies defined, let's see how this builds into the specific math required for rotation. We're going to need a new tool here, the cross product. Unlike scalar products which just spit out a plain number, vector products create an entirely new vector that is perfectly perpendicular to the plane of the first two. And to find its direction, you use the right-hand grip rule. So if you have vector A and vector B, you physically curl the fingers of your right hand from A toward B. Your thumb immediately points in the direction of your new vector C. This little hand trick is the absolute key to understanding the direction of rotational forces.
Now listen up, because here is a massive exam trick you'll want to remember. Order matters immensely in cross products. Swapping the vectors completely reverses the direction of the result. With standard numbers, we all know 3 times 4 is the exact same as 4 times 3. But with cross products, A cross B is the exact negative of B cross A. If you curl your fingers from B to A instead, your thumb points downwards instead of upwards. It's a small detail, but a total game changer. Section 3. Torque and angular momentum.
Equipped with the cross product, we're ready to define the actual physical quantities driving rotational motion. Torque is essentially the rotational equivalent of force. It's calculated by taking the cross product of the position vector, r, and the force vector, F. Think about trying to push open a really heavy solid oak door. You're definitely not going to push near the hinges, right? You push at the handle, as far away from the axis of rotation as possible. That distance from the hinge to the handle is your vector r. By crossing r with the force F that you apply, you generate torque. It is literally the twisting power that causes angular acceleration.
And in a very similar way, angular momentum for a particle is the cross product of its position r and its linear momentum p.
This basically tells us the state of its rotational motion. If linear momentum is mass times velocity, angular momentum captures that linear momentum and multiplies it by the distance from the rotational axis. To get the total angular momentum of an entire rigid body, you just use vector addition to sum up the individual angular momenta of all its tiny particles. Simple as that.
Part 4. Mechanical equilibrium explained. So what happens when we want a rotating system to stay perfectly still, to be totally balanced? Well, here's your perfect mental checklist. For a rigid body to be in true mechanical equilibrium, it requires a dual balance, zero net force and zero net torque. You see, a simple point mass only had to worry about forces, but a rigid body, it can be pushed in equal and opposite directions, meaning the total force is zero, but if those pushes are applied at opposite ends of the body, it's going to spin. That's exactly why the sum of the torques must also equal zero. When both are balanced, neither the linear momentum nor the angular momentum can change with time.
All right, Section 5, Inertia and Rotational Analogies.
Okay, this is honestly my favorite part. It's the ultimate aha moment, where we map translational mechanics directly onto rotational mechanics. Just look at this beautiful pattern. The moment of inertia, represented by I, acts as the exact rotational cousin to mass. It dictates how a body resists changes in its rotational speed. Think about the equations. In a straight line, kinetic energy is 1/2 m times v squared. In a circle, you literally just swap out the variables. It becomes 1/2 I times omega squared. Every single linear concept you spent weeks learning translates flawlessly into rotation, just as long as you swap out mass for the moment of inertia.
But there is one vital difference we have to talk about. Unlike plain old mass, the moment of inertia heavily depends on exactly how that mass is distributed away from the axis of rotation. This is cleanly summarized by a parameter called the radius of gyration, where I equals m times k squared. So if you're spinning in an office chair and you throw your arms out wide, you are distributing your mass further from the axis. That increases your radius of gyration, which therefore increases your moment of inertia. So remember, it's not just how much stuff you have, it's exactly where that stuff is located relative to the spin.
And finally, Part 6, Conservation and Final Review.
Let's bring this all back to the real world to wrap up our explainer. A really brilliant everyday application of this is the flywheel inside an automobile engine. A flywheel is essentially a massive disc whose huge moment of inertia strongly resists sudden changes in speed, which prevents jerky motions and guarantees you a smooth ride. Because this heavy disc's mass is intentionally distributed far away from its axis, it stores a tremendous amount of rotational kinetic energy. When the engine fires and gives uneven pulses of power, the flywheel's massive inertia smooths those pulses right out. It practically acts as a mechanical battery for rotational motion.
So, the really crucial takeaway here is that if the total external torque on a system is zero, the angular momentum is perfectly conserved over time. This brings everything full circle for us. Just like an object in linear motion stays in motion without an external force, a spinning object will conserve its angular momentum perfectly unless an external torque acts upon it to slow it down or speed it up.
So I'm going to leave you with that thought to ponder the next time you look at rotating objects in your daily life. I really encourage you to review these formulas to see the hidden physics in motion all around you. Every single time you swing open a door, watch a car wheel spin, or see a toy top wobble, you are watching the center of mass, cross products, and moments of inertia perfectly at play in a mechanical ballet. Thank you so much for learning with us today on this explainer, and keep questioning the physics of the world around you.